Hi, welcome to another episode of Broadcast Engineering, a series of sorts of things that are very common yet misunderstood by many. So, please join me in discussing some of the simple matters that matters the most when we plan for broadcasting. One of the major points of discussion among engineers implementing digital TV is the different approach in terms of the power to be utilized. Back in the old days, when we talk of analog broadcasting, power is key. But then things changed when we shifted to digital TV. And I'll show you some examples on why digital TV makes it simpler and more efficient. Well, not simple, but more efficient in terms of the power utilization. I have made several coverage examples to show you the difference when we start with low power 500 watts going to 1000 watts and then going to 2000 watts or 2500 watts, then to 5000 watts, and then to 10,000 watts ERP. Okay. If you've noticed, the increments of the ERPs of the examples I've mentioned doubles in comparison. So from 500 watts, it goes to 1000 watts, and then 1000 watts to 2000 watts. Also, I'll show the impact of varying antenna elevation, the receiving antenna, for the same ERP levels. So based on standard, we are using 10-meter height for the antennas. Now, how about those antennas that are lower? So our example will be 3-meter height of the antenna, receiving antenna. From the example, you will see that when we compare a 500 watt ERP to a 1000 watt ERP for a receiving antenna at 10-meter, the difference numerically or logarithmically is only 3 dB. And you will see that the impact is only felt at the fringe or at the edge of coverage. So there will be a minor improvement. The same will be observed when you look at a 1000 watt compared to a 2000 watt, and then a 5000 watt to a 10,000 watt ERP. Next would be we will lower down the antenna height of the receiver and observe the difference of the performance in terms of coverage for the same power levels, 500 watts to 1000 watts to 2000 watts, 5000 watts, and to 10,000 watts. Notice the change in the propagation or the theoretical or simulated coverage has significantly lowered just because of the change in the receiving antenna height. So from this, you will have an idea of how the signal behaves now in terms of reception when the antenna height is lowered. So we're just talking about two factors here, the ERP and the antenna height. With these two factors, you will gain significant understanding on how to plan your coverage. So it's not just put a high power and transmission system in one location and then that's it. So these are two of the relevant uh, parameters that you should consider. Consider the height of the receiving antenna to match with your planned ERP. But if we in this episode, we'll be basing our discussion with several parameters. First would be the ERP for each at 500 watts, 1000 watts, 2000 watts, 5000 watts, up to 10,000 watts. And the assumed transmitter antenna height is around 70 meters, and the receive antenna height are 10 meters and 3 meters respectively. The 10-meter would be the standard and the basis of the NTC channel plan. And then we have also 3 meters as, uh, as an assumption for typical rooftop reception. The received signal level would be 51 dB microvolts per meter, and the assumed transmitter location, which was arbitrarily selected, is Quezon City, and the intended service area is NCR or Mega Manila, depending on the power. The particular standard references from the International Telecommunications Union will be the ITU R1546-5, which is the method for point-to-area predictions for terrestrial services in the frequency range of 30 megahertz up to 3 gigahertz. And then the other one is ITU 1368-13, which is the planning criteria including protection ratios for digital terrestrial television services in the VHF and UHF bands. And then the ITUR BT 2035 is guidelines and techniques for the evaluation of DTTB or digital terrestrial television. And then for our local regulatory standard from the National Telecommunications Commission, Memorandum Circular 07-12-2014. This slide compares the coverage of a 500 watt ERP to a 1000 watt ERP station. Notice the slight difference in the extent of their coverage. The green shows here a reliable signal, and then the red shows you the fringe area. So if you would notice, the one on your left is the 500 watts, which has a distance of 28 kilometers for the green, and then for the 51 dB microvolts per meter is your 38 kilometers. Now, if you increase or double the power from 500 watts to 1000 watts, the difference would be around an increment of 4 kilometers only at the fringe. So from 38 kilometers, yung red will be increased, the range will be increased to 42 kilometers. When we compare 1000 watts increased twice to 2000 watts, notice that the fringe 42 kilometers for your 1000 watts would become 48 kilometers when you double the power. So that is a 6 kilometer improvement on the fringe. And now, from 2000 watts increase to 5000 watts. You will see that the fringe for the 2000 watts is 48 kilometers, and then you will have an improvement of 6 kilometers, so it becomes 52 kilometers at 5000 watts. And then if we compare 5000 watts to 10,000 watts, or doubling the power, the improvement will be from 52 kilometers to 56 kilometers, an improvement of about 4 kilometers. So the picture shows you the slight improvement when you double the power. This time, we will lower down the receiving antenna height. So the previous comparisons are based on a 10-meter antenna height for the receiver, which is our basis for the standard. Now, if we assume 3 meter typical rooftop, not really a standard elevation, but we ran the simulation so that you will have a reference comparison. So this time, you will see that the fringe for the 500 watts become 28 kilometers only, with sporadic, very random distribution, with pockets of below than 51. So we'll just assume yung 51 dB microvolt. So we'll just assume 28 here as an average. And then for 1000 watts, you will see it's around 38 kilometers. Moving to the comparison of a 1000 watt to 2000 watt ERP at 3 meters receiving antenna height. So the 38 kilometers fringe of the 1000 watts, to the 42 kilometers of the 2000 watts. So a difference of 4 kilometers. And now 2000 watts to 5000 watt comparison. So the fringe for the 2000 watts is 42 kilometers, and for the 5000 watt is around 49 kilometers. So this is an improvement of around 7 kilometers. This now is the comparison for the 5000 watt to 10,000 watt. So the 5000 watt ERP, the fringe coverage is up to 49 kilometers, while for the 10,000 watt ERP is about 51 kilometers. So the improvement is just 3 kilometers on the fringe. I'm showing you a table that compiles the data for the 10 meter with varying transmit ERP, and for 10 meters and 3 meters antenna height of the receiver. You will notice that the impact of the decrease of the receiving antenna height and the extent of coverage results into, for example, 500 watts will be equal to 500 watts at 10 meter receiving antenna will be equivalent to the 1000 watt at 3 meters. So this illustration shows you the impact of the varying receiving antenna height for your consideration in your coverage plan. But when it comes to your transmit power, the impact will be minimal, and it will only be felt on the fringe areas, not on the nearby areas or your immediate area of intention. So I hope that this would help you in understanding the significance of doubling your power and what is its impact to your coverage. So is it worth it to double your power just to gain about 4 to 6 kilometers at the fringe? Or should you consider putting another station on a different location to further enhance your coverage and utilize SFN? So I hope you learned something new and relevant today after watching this video, and I hope it would help you uh, gain more understanding so that it will help you plan your network moving forward. There are other things that we will be covering in the future, so I hope you stay tuned. And sabi nga aral lang ng aral para madagdagan ng kaalaman. This is Engineer James, Broadcast Thoughts 101.